This is a review for the third exam in Comp 375 Computer Architecture and Organization at North Carolina A&T State University. The third exam will be on Wednesday, April 22nd from 11 to noon. You've got to be logged on to Blackboard at that time. It will end at noon. Your format will be very similar to previous exams, although you will be able to back up and see previous questions. Please fill out the course evaluations. They're available on Blackboard. Only one student in 375 has completed the evaluation. Get with the program! Please evaluate all of your classes. Here are the topics that will be covered on the third exam, along with the chapters in the online textbook that speak of that material. You would be wise to read the online textbook. The exam will cover bus transfer times. Here's an example. Say we want to transfer 96 bytes over a 128-bit bus. There's a 4-cycle delay, meaning that for the first 4 cycles, wait for the memory to catch up and it will start transferring on the 5th cycle. Okay, a 128-bit wide bus is 128 divided by 8 or 16 bytes. We can transfer 16 bytes at a time. So if we want to transfer 96 bytes, you can do it 16 bytes at a time. Just divide and you get 6 cycles. Now we have a 4-cycle wait time, so we add the 4 cycles for a total of 10 cycles. Try it yourself. Pause the video. Okay, here's how we might possibly work a solution on this. First of all, we have a 64-bit wide bus. And since it's easier if we always use the same units, we're going to convert bits to bytes simply by dividing it by 8 bits. So we find out that we can transfer 8 bytes in a cycle. If we have 16 bytes we want to transfer, you can do 8 bytes in a cycle. It only takes 2 cycles. There's a couple cycles transfer time, so we have to add the 2 more cycles to get a total of 5 cycles. When you have to calculate how long it might read on an average to a piece of information from a disk, there are 3 major components. First one is seek time. That's how long it takes for the head to move in and out to get to the proper track. Then rotational delay is how long it takes for the disk to spin around and for the information to come under the head. And then transfer time is the amount of time required for the data to move under the head and be recorded or read. Since we're often given this rotational speed as revolutions per minute, we can calculate how many milliseconds per revolution by simply dividing 60,000 milliseconds per minute by the revolutions per minute and get the value of milliseconds per revolution. Our answer on these kind of questions are typically going to be in milliseconds, so we'll use milliseconds as our unit. You have to figure out how many sectors you're going to need to read the whole file. So you simply divide the file size by the number of bytes per sector. And then you have to round up. It's important to round up because you can't read half or part of a sector. The rotational delay on a drive is simply half the rotation time. If you're lucky, the information is just coming under the head as you finish seeking out to that location. If you're not very lucky, the data will have just missed and you have to wait for an entire spin to get around. But on the average, from 0 to a full spin, is half a spin. So we'll use half a spin as the average time. The transfer time is the number of sectors per file, which we calculated earlier, divided by the sectors per track, which is given in the tech and specifications, multiplied by the spin time, which we calculated. That gives you the transfer time. Here's an example. We'll use this information from our hard drive. Okay, we want to read 161 kilobytes. Now this disk is rotating at 10,000 RPMs. So we take the 60,000 milliseconds per minute, divide it by 10,000 revolutions per minute, and we get 60 milliseconds per revolution. Then to calculate how many sectors we need, we simply divide 160 by 4. Now that gives us 40.25, but you have to round up to 41. You have to have an integer number. Then we just add the seek time, the rotational delay, and the transfer time. The seek time was given to us as 5.3 milliseconds. The rotational delay on average is half one rotation, so half of 60 is 3. And then the transfer time is the 41 sectors divided by 127 sectors per track, all multiplied by the 6 milliseconds per revolution that we calculated, and we get the number 1.9 milliseconds. Add it all up, and you get 10.2 milliseconds as an average time to read that data. Figure it out for yourself. Okay, we have, again, 10,000 RPM. Not that 10,000 RPM is a common value, but it's an easy number to calculate. So we divide 60,000 milliseconds by 10,000, we get, again, 6 milliseconds per revolution. We have 45 K on the right, so we divide that by 4. Rounding up, we get 12 sectors. The seek time was given to us as 5.7 milliseconds. Divide that 6 milliseconds by 2, and we get 3 milliseconds rotational delay. We calculated 12 sectors, divide that by the 255 sectors per track, and then multiply the result by that 6 milliseconds of rotation time, and we end up with 0.28 milliseconds. Add all the values together, rounding off to the nearest tenth of a millisecond, and we get 9 milliseconds. Don't forget to round up the number of sectors. Disks are read and written in even unit sectors. There'll be a question about RAID disks. There are several different RAID formats. These 4 are the most common. RAID 0 is simply striping. It provides no redundancy, and so it requires n disks. Where n is the number of disks to hold the data, then it requires exactly that much. But if there's any failure, you lose all your information. RAID 1 is mirroring. It requires twice as many disks as would require to hold the data. It will survive the loss of one disk. Reads are slightly faster because it can read from either drive, but writes are slightly slower because it has to write to both drives. RAID 5 is parity, and you need only one additional disk to do that, and it can survive the loss of one drive. If you need to survive the loss of 2 drives, you can use RAID 6, which requires 2 additional disks. The general strategy for figuring out which RAID system and how many disks is to first figure out how much does your data take, how many records, how big is each record, figure out how much data you have, and then divide that by your disk size to figure out how many disks does it take to hold the data. Make sure you round up because you can't have half a disk. Once you've got the number of disks, if that number is less than 1, well then use RAID 1 with 2 drives. That's mirroring. If, though, it takes more than 1 disk to hold the data, then add 1 disk and use RAID 5. Unless you're really paranoid and you want to survive the failure of 2 drives, then you add 2 more disks and use RAID 6. Try this. Here's the solution. Okay, we have 2 terabytes, which can be thought of as 2,000 gigabytes. So we divide that by 800 gigabytes, and we get 3. 3's, and we have to round up. We get 2.6, but we have to round up and get 3 disks. So since 3 is bigger than 1, we'll use RAID 5, and we add 1 disk. So we'll take 4 disks using RAID 5. Don't forget to round up the number of disks. You can't have half a disk. Hazards are situations that tend to reduce the performance of pipelining and superscalar execution. They don't cause incorrect results in most machines, but they do cause them to run slightly slower than they otherwise would. There are 3 types of hazards. A resource hazard occurs when there's just not enough of a particular resource for the machine to run things in parallel. There may not be enough arithmetic logic units or maybe enough paths to memory in order to do the 2 operations in parallel. A data hazard occurs when one instruction is changing information that is going to be needed by the next instruction. the write back step of the instruction is the last step, and if a following instruction needs the information before the write back is complete, it will have to wait to get that information. And a control hazard occurs only when there's a jump. During pipelining, we are fetching instructions all the time, and by the time the hardware figures out that this instruction is a jump, they've already fetched and processed some of the following instructions, which will then have to be discarded because we're not going to be executing those. We're going to take the jump. Consider a resource hazard here, where the resource is the paths to memory. We have multiple instructions running at different time cycles. In this example, we have 5 cycles per instruction. The instruction fetch, the instruction decode, the operand fetch, the instruction execution, and then the write back. On the third instruction, it would like to do an instruction fetch at that time if it could, but we'll assume that there's only one path to memory, and instruction 1 is fetching the operand from memory at that time. Therefore, we don't have enough resources to fetch the instruction and the operands at the same time. So the third instruction is idle or has a pipeline stall for 1 cycle. So instead of starting on cycle 3, we'll have to start on cycle 4. Data hazards occur when a register value is being modified by one instruction, and then the result is needed in the next instruction before the first instruction would otherwise write the information back to the register. In this example, the add R2, 7 would normally write the result back to register R2 on time 5. But the subtract instruction will want to be fetching the operands in time 4. But the operand, the updated R2 value is not available until the next cycle. So this will cause a pipeline stall. There are a couple ways to fix this. One is register forwarding, where the information coming back from the arithmetic logic unit can be fed directly into the result register for the next cycle, or register locking, which doesn't really fix the problem, but it keeps you from getting errors. When a register is being changed, it locks it, and then a following instruction will not be able to access the locked register until it's released by the previous instruction. Control hazards are caused by jump instructions. As the machine is pipelining, it continually fetches more instructions. So by the time it figures out that one of the instructions is a jump, it's already fetched some of the following instructions and started to process them. But because the jump instruction changes the flow, the following instructions will not be executed, so they have to be discarded. This wastes some of the processing time. The pipeline is transparent to the high-level language programmer. You don't see it at all. On the other hand, if you're writing an assembler program, you can write programs that are inefficient or efficient to work with pipelines. If you have lots of opportunities to cause stalls, the machine will run slower than if you optimize and avoid the stalls. Compilers are very good at rearranging instructions to avoid data hazards. Typically, if you turn on optimization, it will try to rearrange the instructions for better pipelining and superscalar execution. Here's an example of rearranging the code. On the left, we have the same result as we see on the right, but now the machine has been optimized. If you notice the first one, we go load something in the EAX register, change it, store it, and then load something in the EAX register. Well, you notice that we are changing the register that we needed previously. The add EAX, pig is changing the value, and so we keep getting data hazards. On the right, we're using more of the registers. So we move rat into A, dog into B, and cat into C. And then we change A, and then we change B, and then we change C. So we keep using different registers and avoid the pipelining issues. Well, we were avoiding data hazards. Data hazards occur when one instruction is modifying the information needed by following instructions. We didn't have any resource hazards because we were doing the same instructions. Control hazards only occur when there's jumps. RISC systems are reduced instruction set computers. try to make the machines run faster by executing only simple instructions. They don't implement the more complex instructions seen in CISC or complex instruction set computers. They typically have register-to-register operands. Only two instructions, the load and the store, access memory. Everything else has only register operands. So instead of having something like add EAX, dog, where dog is a memory location, you'll have add R3, R7, R2, where all the registers contain the operands. They also have simple addressing modes. If you remember from your microcode, the addressing modes were what made it complex. RISC machines typically have a large number of registers, so you can keep all those operands in the registers. They have fixed length instructions. If you remember from the microcode, we incremented the program counter before we actually got the instruction. That's because we assumed it was a fixed length instruction. If it was a varying length instruction, we wouldn't know where the next instruction started until we decoded the first one. And because they have fixed length, there's typically a simple instruction format. They only have one format. If a field isn't needed, you just leave it blank. They try to start instruction every cycle, so they will, in effect, execute one instruction every cycle. Simple instructions are easy to pipeline. They also use delayed branches. A delayed branch means that when the instruction is a jump, the following instruction, maybe next two instructions, are always executed. So a jump doesn't mean jump now, it means jump after the next instruction. That way, the next instruction, which has already been processed by the pipeline, gets a chance to be executed and all that processing isn't lost. Here are some traits of RISC processors. Now the first one, pipelining, is also a trait of many modern complex instruction set computers. But the other features are pretty much items that we only find in RISC processors. RISC machines typically do not use microcode. They hardware implement the instructions instead of using microcode. So the answer would be B. Increased reliance on microcode is a feature of complex instruction set computers. There are various types of parallelism that occur in computers, and some of it is invisible to the high-level language programmer, and some of it is visible. For instance, superscalar and pipelining. Programmer in a high-level language never knows it, and programs will continue to work correctly even if you write assembler that's sloppy, although you can improve performance by writing more efficient assembler. Multiple threads. If you want to run multiple threads, then the programmer has to be very aware of that. You'll have to execute instructions that create multiple threads. Multiple processes may or may not be visible. If you're using processes very similar to how you might be using threads, some programs have multiple processes, some have multiple threads, then the programmer will be very aware of it. On the other hand, if you're writing a program and you don't have to think at all about what other programs might be running on the computer at the same time, then it's completely invisible to the programmer. Many years ago, Flynn came up with a classification for different types of computers, and we're still using that. It's important to know the classification because you see these letters in many places. There's single instruction, single data. That's your standard old-fashioned uniprocessor that executes one instruction with one piece of data or one pair of data. Single instruction, multiple data is like a vector processor where it picks up lots of data and does one operation on all the different data. For instance, you might have an array of floating point numbers and you add it to another array of floating point numbers, all with one instruction. The machine picks up all the array, adds it to another array, all in one instruction. Multiple instruction single data is relatively rare. Those are systolic processors. And then multiple instruction, multiple data is probably the most common type of multiprocessor system, where you have multiple processors, each executing separate instructions with separate data. Most programs execute one line at a time, and we're then running a single instruction on single data. If you have 2 or more cores in your machine, then you'd be running multiple instructions. They are separate instructions, each running on separate data. Your standard Intel instruction like add EAX, dog is operating on only one pair of values. You're only having one data value, single data, whereas some machines allow you to operate on multiple data values all at once. That'd be multiple. Our old microcode computer is a single instruction, single data machine. It picks up one instruction, one piece of data, and works on that, and then goes to the next instruction. Older computers, before we started getting into all the other features, were single instruction, single data. For single instruction, multiple data, as we mentioned, vector processors. The Intel MMX instruction set operates on multiple integers at once. You can pick up a 64-bit value and consider it to be 8 bytes, and then you could add those 8 bytes to another 8 bytes and act on that as a single instruction, multiple data. Multiple instructions, single data are very rare. We don't generally use those, although sometimes in signal processing machines you'll find these. And then multiple instruction, multiple data, SMP is shared memory processor or symmetric multiprocessor. This is very popular. These are your dual core machines that you find in laptops these days. Multiple instruction, multiple data, separate memory are machines where each processor or each group of processors has its own memory. In that way, the bus is not overwhelmed as it's transferring information between memory and all the different processors. If each processor has its own memory, then there's no contention for that CPU getting to the memory. In a separate memory system, the different processors communicate with each other over special I/O channels. This would be a multiple instruction, multiple data, or CMIMD machine. Flynn may just show up on the exam. Be sure to know the different types. Here are some highly probable questions, figuring out how long it's going to take to transfer information across a bus. Again, figuring out how long it takes to read some information from a disk. What is the appropriate RAID configuration and how many disks will you need for a given situation? Specifying Flynn's classification for different types of computers, and defining the attributes of RISC processors. So these are highly likely to be on the exam. Highly likely, you can count on them. Good luck on your exam. The third exam is at 11 to noon on Wednesday, April 22nd. Be logged on to Blackboard at that time. Sure to do the course evaluations for all of your classes.